Hi, this is Math 1428, Remote Delivery. For April 24th, 2020, we're covering Section 6. I've been thinking a bit about teaching and learning in the era of COVID-19, and I'm finding that teaching involves more preparation and rendering of material. But learning is more student-centered. That's not necessarily a bad thing. I steer the bus, primarily, but the student, by using keys like this on the YouTube video, controls both the throttle and the transmission. You can rewind, you can freeze frame, and the student provides most of the learning horsepower. I want you to know that I am proud of your efforts. If at all your circumstances permit, I encourage you to stay the course. It is what champions do. Your educational goals need not be deferred. Today's topics are from section 6.4, and we will talk about add, subtract, multiplying matrices, and how to write a matrix equation equivalent to a system of equations. So this is what a matrix looks like. You have rows and columns. Now the I always represents the row and the J represents the column. So you see this is the first column, and the second digit is always ones, but this is the first row, second row, third row, and mth row. Similarly, going across here, this is first row, first column, first row, second column, first row, third column, and first row, nth column. The matrix above then has m rows and n columns, and so the order is, the dimension of the matrix is m times n. Two matrices are equal if they have the same order, and every corresponding entry is equal. We add or subtract matrices by doing it term by term. And again, you have to have the same dimension matrices in order to add them. Here's an example. Both of these have the same dimension matrix, so we can add them and get an answer that is the same dimension as the two things that you were adding. You can do this on your calculator also. And here's a problem you can use to test your understanding. Similarly, we can subtract two matrices. Again, the dimensions have to be the same. Now in B, notice that the dimension is not the same, and in B you would get an error, or I would say you can't do this. For C minus D in the first one, though, you should be able to get this. Again, here's an exercise that will allow you to test your understanding. Instead, we have a number in the real number system that is 0, and if I take 5 plus 0, that's the same thing as 0 plus 5, and it's equal to 5. Well, in matrices, you have the same thing. So a matrix having zeros for all its entry is the zero matrix. It's called the additive identity because if you add 0 to a matrix, you will get the matrix that you started out with. So this is the matrix 0. It does depend on the dimension, though. You have one 0 matrix that is different for each dimension. We also have an operation called the scalar product. So if you take any number, and this is just a number, you can multiply it times a matrix, and you will multiply by each entry in A by the number in K. So for example, here I'm taking 3 times A. So if I take this as A and I multiply that by 3, I get this expression. And similarly, if I take minus 1 times A, I will get this expression. And these can be found on a graphing calculator. And I encourage you to try this exercise to test your understanding. Many of the properties are the same as real numbers. Let's talk about an example. So you have a company that makes 3 types of kayaks. These are like little canoes. And they make them at a Madison plant and a Greensburg plant. A matrix provides you an easy way to store this in a computer. So that represents all the information in the table is represented this way. You're only storing these numbers in the computer. Now, Part B says the manufacturer wants to increase production by 20% in May, and so that's found by the scalar multiple. We take 1.2 times this, and I get this is the production in May. And then they want you to add A and M. We do this, and computers can do this very fast, and you'll get this result, and this you're supposed to interpret it as well, and this represents the total production of each of the 3 types at each plant. And there's an exercise that you can try to test your understanding. When we multiply matrices, though, we do it differently. The matrix, first of all, the matrix product is not always defined. The number of columns in the first matrix has to equal the number of rows in the second matrix. And when I take an M by N matrix times an N by P matrix, I get an M by P. So it's the number of rows of the first one and the number of columns of the second one. We can only multiply matrices whenever the number of columns in the first matches with the number of rows in the second. So here are some examples for these products. We have A, B, and C here, and so we can do those multiplications and get these answers. This one is defined because the number of rows equals the number of columns. So that is defined. You should get this answer. Here, this is B times A. So the number of rows is 3, the number of columns is 3. So that is defined. And this is your answer, and it would be a 3 by 3. Here, but notice that this, B times A, does not equal A times B. That means matrix multiplication is not commutative. But that's something that is different, and you want to keep that in mind. You can also do this with your calculators as well. And so the last example, this is what you get. And A times C is, again, not defined, because here you have 2 rows and 3 columns, and here you have only 2 columns. So that is not going to be defined. Here's an exercise you can do to further test your understanding. So here we have a bakery, and the bakery makes bagels and donuts, and they have 3 locations. So this can represent this. And the bakery's profits are different on these. The profit on 1 dozen bagels is $5, and on 1 dozen individual bagels, and its profit on 1 dozen donuts is 6. These are in units of, they're only selling things in dozen. So use matrices to find the total profit. Well, what you're going to do is you're going to multiply this. Now this is 1 row and 2 columns, and this is 2 rows, so it matches. So you're taking this times this, and you're going across, and you get this. This represents the total product on bagels and donuts at each of the 3 stores. Here's an exercise you can do to test your understanding. And we can talk about a matrix that consists of a single row. This is often called a row matrix, and this would be the one that we just talked about is row matrix, the 5, 6. This also is a single column. This is called a column matrix. And the properties of matrix multiplication we know about. Now, what happens is, though, if you think about matrix multiplication, you can represent this system of equations with this matrix equation. You see, this is a column matrix representing the right-hand side. If I take this matrix times this matrix, this is 3 rows and 3 columns. This is 3 columns. So the answer is going to be, I will get actually all of these things, because this times this will be equal to 3. This times this will be the 5, and this times this will be the 1. So you see, we now have a matrix equation that is AX equal to B. Here's an exercise you can use to test your understanding. That's the end of part 1. See you in part 2.